So we saw what the problems were with the vicious cycle theory of free radical aging. So now that we understand that, let's have a look at what people hypothesize is going on today. In order to do that, we need to look at how energy is generated in the cell. We'll go over that very quickly. Most people will know this already from general biology. Sugars undergo glycolysis and give pyruvate. Pyruvate and all the other carbon compounds enter the citric acid cycle. They are turned into carbon dioxide. We breathe that out. And the end result is more ATP and electrons. And the electrons are loaded onto this electron carrier, which becomes NADH. So it's carrying 2 electrons here. This is then taken to the electron transport chain. And through the electron transport chain, oxidative phosphorylation happens, where the bulk of the ATP is generated in cells. But it's important to note that these electrons are dropped off. So NAD plus is regenerated. So now that we know this, we've gone over this very quickly. If we recall, in mutant mitochondria, they do not generate free radicals in their mitochondria because they're not undergoing oxidative phosphorylation. If they're not undergoing oxidative phosphorylation, and only 1% of cells have mutant mitochondria, 1% of cells have mutant mitochondria in advanced age. How does this 1% export damage to the rest of the body? That's the question, because clearly from experimental results, if we lower the incidence of mutant cell generation by adding catalase and other antioxidants and different gene manipulations, the result is a significant extending of lifespan. So clearly this is doing damage somehow. But also we know about free radicals is that they react very quickly with whatever it is they're going to react with. So even if a radical is generated, it's not long for this world. It's not going to have, if I have a mutant mitochondria in my foot, it's not going to get to my brain at all. It's going to react to something long before it gets there. So how are these 1% of cells exporting all this damage? In the old theory, all cells were getting slightly worse and slightly worse and slightly worse, so all of these cells were accumulating slightly more damage. As we saw, that was not the case. So let's have a look, and what we're really going to be paying attention to is NAD+, not really that, but electrons. So this is not working. The cells still live, though, because they're able to get ATP from the citric acid cycle and from glycolysis. But this works. For this to work, it needs NAD+, because it needs to give away electrons. And for this to work, it needs NAD+ as well. The problem is that the cell is not generating NAD+, because it's normally recycled. Once these electrons are given to the electron transport chain, NAD+ is regenerated. So in order for this to keep going, it needs to somehow regenerate NAD+. And in order to do that, it needs to get rid of electrons, essentially. It's to dump electrons. And there is a cell mechanism by which it can do that. It's called the plasma membrane redox system. It's on the outside membrane. And what happens here is that all the excess NADH goes to the plasma membrane redox system, and it's able to offload its electrons and thereby regenerate itself to NAD+, so it can continue the citric acid cycle and glycolysis. But since there are so many more NADHs now, it doesn't necessarily have to be NADH that gets rid of the electrons here, but there are going to be so many more electrons going to the plasma redox system now that it's going to have an area. They're called reductive hotspots, essentially. And basically, it's an area that has a negative charge now because there are more electrons there than there should be. So these can get picked up by antioxidant electron acceptors and be dealt with normally, but they can also be picked up by other things, such as oxygen. And as a result, we can create that superoxide ion that we talked about last time. And this can be dealt with by antioxidants as well. There are different cellular defenses that can turn it into things such as water or something else that can react with it that will stabilize it. But what can also happen is that it can be picked up by a different carrier molecule, low-density lipoprotein. This is what people call bad cholesterol. And it's not really bad. It's in normal quantity. It's essential for the body's function. These carry around lipids, cholesterol, things like this for other cells. It's like a delivery truck, essentially. But it's got organic metals and different things on there. But what can happen, though, is that this can react with the low-density lipoprotein and become oxidized. And when it's oxidized, it then travels throughout the body, and it can go into different cells. And when the cells receive it and get whatever it is they're normally getting, they're going to be getting a lot of this stuff as well, and that can cause damage over time. So this is the idea of how damage in the mitochondria can cause a backup in the supply of NAD+. So it causes a shortage of this, and in order to rectify that, the cell begins dumping electrons, and as a result, what can happen is accidentally, because there's going to be a lot higher volume than normal, accidentally it can be picked up by things like oxygen, and oxygen can react with something else, and something like low-density lipoprotein, they already have, this is a process that's already been brought up in things like arteriosclerosis, where we'll have oxidized low-density lipoproteins causing damage. These things get taken into cells, and it's kind of like a letter bomb, essentially, and it does damage. They can be dealt with by different cellular defenses, like macrophages. They can get rid of them, but this basically, but still some are going to get through. This is basically the idea of what's going on with the mitochondrial free radical theory of aging as of today. Maybe it'll change, but it seems very plausible.